Good evening, ma'am.
Hmm. I hope I'm audible. Okay. Yeah.
Yes, ma'am.
So now it is not getting echo, na? Yeah. Okay. So today we'll be solving some problems related to Lebesgue integral. I hope now you are comfortable with the theory related to Lebesgue integral, integral of functions, integrable functions. Anyways, I'll keep explaining the basics that's required for those things as well. So, the basics that you should be already aware of is the Riemann integrability. I hope that you must have done in your graduation, na? Riemann integral.
Yes, ma'am.
Okay. Okay. So, yeah, there are many functions that are not Riemann integrable, and but we wanted them to be integral. We wanted to evaluate their integral because yeah, somewhere it was needed. So eventually we developed the theory of Lebesgue integrable functions, which involves which is a bit bigger class of functions. So let's start with one of the exercise in the class. Find a sequence of Riemann integrable continuous functions. A sequence of Riemann integrable functions. In particular, we want to find some a sequence of continuous functions defined on closed and bounded interval. We all know that continuous functions are integrable on closed and bounded intervals. Continuous functions defined on some interval close AB such that the pointwise limit of the sequence, or I should write whose, whose pointwise limit is not Riemann integrable. So did you look for some functions, some sequence, some example? Okay, so I'll give you one example. So let's start with the assumption that without loss of generality, let A, B be some positive real numbers. We can similarly construct a sequence for a negative as well. Not a big deal. So now we'll be using the fact that the set of rationals, it is a countable function and hence we can enumerate it. Since Q, the set of rationals, is countable, it we can it can be enumerated. That means we can write the elements in the set in, or we can define a map from set of natural numbers to the set of rationals. It can be enumerated. This implies closed interval AB intersection Q, if I take out the rationals in the set closed interval AB, then also I can write to the subset of Q is also countable and hence can be enumerated. No, even I don't have notes. Even I'm uh, all I have is that what is on the web page, so I don't have anything else. But yeah, I'll try to follow whatever basics that will be required, at least for the problems I'll be doing today. Is also countable and hence can be enumerated. Okay, that means uh, now suppose the enumeration is as follows. Suppose we can write Q intersection close interval AB. This is equal to the set x1, x2, x3, and so on. We'll see how this will be useful. Okay. Enumeration of Q intersection. Now we'll define a sequence of function. Now define, or I would say rather we'll construct. Let us construct a sequence of continuous functions. Define F1, our map F1 from close interval AB to R is such that its graph uh, is given by, if suppose this is A, this is B, you can write the explicit form. So suppose x1 is somewhere in between, obviously it is somewhere in between A and B. So I construct f1 is such that at x1 it is equal to 1 and then it is a triangle. So basically it is a piecewise function. From A to x1 it is the straight line this. I think you can write the equation for that straight line. And um, for points between x1 to b, it is a straight line. Basically, their slopes will be negative of each other. So yeah, that would be a good exercise for you. Write its explicit form. Okay. Next, we'll do something with the terms x1 and x2. For f1, we used just 1 point x1. Next, we have consider the set x2 to be x1, x2. Now, since x1 and x2 are two distinct real numbers, by well ordering principle, we know that this set will have uh, 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 s- uh, this set has exactly two elements. So yeah, by well ordering principle, it will have a least element, and then removing that point from the set, the next set left. In this case, that would be just set with just singleton set. In that set again we can apply the well ordering principle to get the least value. So eventually we can convert this into a form that I would say x2 bar is y1 y2, where y1 belongs to x2, y1 and y2 both belongs to x2 are such that y1 is less than equal to y2. Clearly, we can do this ordering because we have distinct rationals, and since in real numbers we can compare two real numbers. So yeah, I'm doing this to construct the function f2. Now we'll construct f2 from closed interval a b to r such that its graph can be given by, now suppose this is y1. Yeah, this is why I did this ordering so that I can write y1 before y2. Now again, I want our function to map y1 to 1 and y2 to again 1. So you can see that either of y1 or y2 is x1. So at x1, again the function f2 is 1. Now again, I'll make two triangles. Now these triangles are such that this length, this length m, this is m length, is such that m is equal to minimum of mod a minus y1, y1 minus y2, y2 minus b. So that the function is well defined. Now I hope you must have got the point how we will be constructing further functions. Yeah. So again, I I'll consider x3 to be the collection x1, x2, x3, and x3 bar will be the corresponding ordered form. So I'll write it as y1, y2, y3. This y1 and the y1 above need not be the same, but eventually at all the points x1, x2, x3, the function f3 will also give the value 1, and at rest of the points it will be some triangle. So this is y1, y2, y3, then b. Again, we'll be constructing some. This time, obviously, this length will eventually decrease, but still the function will be continuous. Now this length, this base length m is, I should write it as m2. This will take as m3 will be minimum of mod a minus y1, y1 minus y2, y2 minus y3, y3 minus b. So clearly, all these functions and moving on in such similar pattern, our function fn for some n would be something like this. We'll have a some n number of triangles. So can you tell me the pointwise limit of this sequence? Any idea?
It will be 1, also 0,
Hmm.
and
So where will it be one?
in every rational point, so or the
On
point that we are constructed.
yes, on the rationals it will be 1, and eventually you can see that we are reducing the base length of the triangle, so eventually for all irrationals it will converge to 0.
Oh, yes.
So this will converge to the function fx, which is equal to 1 when x is rational and 0 when x is irrational. And this function has a specific name. This is called
Dirichlet function, I think.
Dirichlet function. Yes, Dirichlet function. And I think you all know about its integrability. So is
It's
it
not Riemann integrable.
does not remain integrable? Dirichlet. Sh- Please check this spelling. I don't remember. Yeah, we know that, but since this f is not Riemann integrable, we are done. Really, clearly, if n is continuous for every n in n. Hence, we got a sequence of continuous functions, continuous Riemann integrable functions whose pointwise limit is not Riemann integrable. Therefore, it is not necessary that if we have a sequence which is converging pointwise, sequence of functions converging pointwise, even though each of the element is integrable, it is not necessary that the limit or the pointwise limit will be integrable as well. So, do you know when the limit we can guarantee that the limit will be integrable? In what case it happens?
Uniform convergence, no?
Yeah. When we have uniform convergence, in that case, we have the limit will be Riemann integrable as well. Okay. So this is a very good example. You should remember many times it is asked in the interviews also. Okay. Mhm. Next, yeah, let's go through some theory of Lebesgue integration. I'll recall some basic definitions. Okay. So what is this? Summation n from 1 to infinity 1 by n. Summation 1 by n diverges.
So integration diverges to it will not be integrable if we consider such function.
Such a function. So basically, you are taking triangles. So in this
Yes,
case, also you'll have to construct a sequence. While writing explicitly, the first function would be the triangle between one half to one, and from zero to half, it should be zero, something like that.
yes,
And the
yes,
second
yes,
function
ma'am.
would be same 1 by 4 to 1 by 2, 1 by 2 to 1, and rest. So it should be multiplied by some characteristic function.
Yes.
Yeah, yeah. In this way, also you can show.
Actually, it is the same idea that we have
Yeah, yeah.
discussed. No? Okay,
Okay.
thank you.
Mm. So yeah. Now let us go through some theory of the Lebesgue integration. So, firstly, what do we mean by step function? I think you must have watched those lectures. So, can you tell me what do we mean by step function?
Step function, it is a function from a interval which is partitioned
Hmm.
and for
Partitioned
each,
by intervals.
yes, sub intervals, and it has functional values fixed at each sub intervals.
Hmm. So, basically, we call it a linear combination of characteristic functions.
Yes,
So, we can write this as a, a function, f, suppose from x being some interval, subset of R to R, be a sorry, function of the form, then we can write it as fx equals to summation I from 1 to n fixed alpha I times characteristic function ai x, where this characteristic AIX means this is equal to 1 for x belonging to AI, 0 for x not belonging to AI, where each AI is an interval such that this union I from 1 to n AI, this is equal to x, and AI intersection AJ, this is empty for every I not equal to j. So this is, yeah, pairwise disjoint. So such a function is called step function. So we define Lebesgue integral over this step function. Then we define integral x of above f, and we write it as d mu, or yeah, we can write dx as well. Dx implies the Lebesgue integral. This is equal to summation I from 1 to n alpha I times length of e int sorry. Now suppose we are integrating over some set e. E can be some subset of x. E intersection a. So this is how we define integral over step functions, and then using these step functions we further define integral of other measurable functions. So have you done measure theory also before this?
Yes,
Some
ma'am. A
uh,
little bit.
so okay, so you are comfortable with the term measurable function.
Yes.
Yeah, so using the integral over the step functions, we can define integral of other measurable functions as well. So we have some properties of this integral of step functions. So we can call it as some theorem or some problem. We'll be proving it. Properties of integral step function. So suppose phi and psi are two positive step functions. Then we have the following. Firstly, suppose it is they are defined on some set x, some interval x, c times phi. This is equal to where c is some constant phi dx for some c in R. Then we have integral over x phi plus psi dx. This is equal to x phi dx psi dx. So in order to, while proving all this, we'll be using the basic definition. Using definition, we'll show this. If phi x is less than equal to psi x for every x in x, then this integral x phi x dx, this should also be less than equal to integral psi x dx. Let's Now, since phi and xi are two step functions, let's write their explicit form. Suppose phi x, this is equal to summation j from 1 to n aj, characteristic function over intervals ej x, and Xi x, this is equal to, this is again linear combinations of some other characteristic functions. So this will be summation k from 1 to m bk characteristic function over the intervals fkx, where union j from 1 to n ej, this is equal to x, which is also equal to union k from 1 to m fk. Also, these ej's and fk's are ej's and fk's are pairwise disjoint. So ei intersection ej is empty for every I not equal to j, and fk intersection fr is also empty for every k not equal to r. So this is how we define as two distinct step functions. Also, for each k, let's start with j, from 1 to n, our ej can be written as x intersection ej, because obviously ej is a subset of x. Now this x can be replaced by union fk. You'll see further how this will be useful. So I can replace this x by union k from 1 to m fk intersection ej. So this can be written as, I can take this union outside, union k from 1 to m fk intersection ej. Similarly, for each k from 1 to m, we can write this fk as union j from 1 to n ej intersection fk. I hope this is clear how I have written these functions ej's and fk's.
Yes, ma'am.
So let's start with first part. Let c be some real number. So this integral over x, c times pi x dx, this is equal to integral over x c times. Now this pi x, this is nothing but summation pi. This is equal to summation j from 1 to n aj characteristic function ejx dx. I can take the c inside the summation. So this is just x summation j from 1 to n caj times characteristic function ejx. Now this is a step function. We know how to integrate step function. So this will be summation j from 1 to n caj times length of the intervals ej. Because if I write it as some phi bar, x equal to summation caj characteristic function of ej at x j from 1 to n is a step function. So this, now this ej can be written as summation j from 1 to n. Okay, so in this case, we don't need anything else. I can take the c outside the summation. This will be length EJ. Now this is nothing but integral over x of function phi x dx. So yeah, we can take the c outside. I hope this is clear.
Yes, ma'am.
Okay. Next, we need to show that the integral of sum is sum of integrals. So this is x phi x dx. Uh, so you want me? I have studied measurable functions from a subset of real numbers, not on general structure. In general, also, what I can remember when we have functions from suppose some measure space x to r, we call this function f is measurable if f inverse a is measurable in x for every open set a in r.
Oh,
Yeah, it's something similar to the continuity. For continuity, we know that open set has a pre-image. Pre-image of an open set is open. In this case, we take that pre-image of open set is measurable. That's the
okay.
main difference between measurable functions and continuous. So the idea basically comes from continuity. This is plus x xi x dx. This is by definition of integral of step functions. This is equal to summation j from 1 to n aj, length of the intervals ej, plus summation k from 1 to m bk, length of the intervals fk. Now we'll use the above relation between ej's and fk's. So I can write this ej. This is equal to summation j from 1 to n aj, length of the set union k from 1 to m. This was fk intersection ej. I'll mark that as star. Plus similarly for fk, this will be summation k from 1 to m bk times length of union j from 1 to n ej intersection fk. Next, I'll write this as equal to summation j from 1 to n aj, summation k from 1 to m, length of fk intersection ej, plus summation k from 1 to m bk times summation j from 1 to n, length of ej intersection fk. Now we can write this as equality because inequality less than equal to we always have, because this length function has subadditivity function condition. But in this case, we'll have equality because okay, we have length of union k from 1 to m Fk intersection Ej. This is equal to summation k from 1 to m. This can be done only if all these sets are pairwise disjoint. Because in case they are disjoint intervals, in that case we can directly add up the length of the intervals. That's what we are doing here. So we are able to do that because for any k not equal to r, we have fk intersection ej. You can see that in this case ej is fixed, intersection fk fr intersection ej. This can be written as fk intersection fr intersection ej. Now since these fk's are pairwise disjoint, this will be empty. Similarly, we have length of union j from 1 to n. We know that when we have union of intervals, we can write L of union of I k's is equal to summation length I k's only if, suppose k from 1 to
IKs are pairwise disjoint.
pairwise disjoint. So that's the main idea how we got this equality. Similarly, we'll get length of union j from 1 to n. This case we had ej, yeah, ej intersection fk.
Or
This
we
will
can
be
say that these intervals doesn't have the common interior points.
interior
And
points. Intervals always have interior points.
two,
What kind?
two, two intervals doesn't have the common interior points.
Common interior point. Yeah.
Oh, yes, sorry.
Length of ej intersection fk. So yeah. Therefore, this is equal to, now since j and k are independent, I can take everything outside. So this will eventually be summation j from 1 to n, summation k from 1 to m, aj, length of ej intersection fk plus summation k from 1 to m, j from 1 to n, or write it in same form, summation j from 1 to n, k from 1 to m, bk, length of ej intersection fk. Now this is equal to, I can write this as in one form, summation j from 1 to n and k from 1 to m. So this will be m j j from 1 to n and k from 1 to m, aj plus bk times length of ej intersection fk. Now these this union j from 1 to n, k from 1 to m, ej intersection fk, this will eventually give us the whole set x, and also they'll and you'll end up getting all these are pairwise disjoint. So this will be equal to integral over x pi plus xi dx. Since for every x in x, now this x is union ej, and this is also equal to union fk. This implies there exists some j belonging to the set 1 to n and some k belonging to the set 1 to m, such that x belongs to EJ and x belongs to FK. Obviously, since x belongs to this union and this union as well, so this implies x belongs to EJ intersection FK. So in this case, phi x would be AJ and xi x would be BK. So eventually, AJ plus BK would be phi x plus xi x for x belonging to EJ intersection FK. Also, any x in X will eventually belong to sum of EJ intersection FK. So therefore, uh, this will eventually phi plus xi will also be a step function. That's what we are showing, and its integral will be same as the sum of integrals of phi and xi. Therefore, we get integral of phi dx plus xi dx. This is equal to phi plus xi dx. I hope this is clear. Next, we will see the inequality part. Okay. Now let phi x is less than equal to psi x for every x in x. We'll show that the same inequality holds for the case of integrals. Now, integral over x phi x dx. This is equal to summation j from 1 to n aj, length of the intervals ej. Now this is equal to summation j from 1 to n aj, length of union k from 1 to m fk intersection ej. Now this is again, as we did earlier, this is equal to summation j from 1 to n aj, summation k from 1 to m, length of fk intersection ej. So eventually this is summation j from 1 to n, summation k from 1 to m, aj, length of fk intersection ej. Now I'm saying that this is less than equal to summation j from 1 to n, summation k from 1 to m, bk, length of fk intersection ej. Now this happens because we know that either fk intersection ej, either this will be empty or obviously non-empty, or fk intersection ej is non-empty. So when this intersection is empty, in that case, clearly this length will be 0 and we don't have anything to do. And for the case of non-empty, that means there exists some x in fk intersection ej. That means x belongs to fk and x belongs to ej. In this case, phi x would be aj, yeah, and xi x would be bk. Now this is a fixed x. We know that for every x, phi x is less than equal to xi x. That means aj is less than equal to bk. So eventually we get this inequality. AJ will be less than equal to BK. Yeah. And this is now equal to summation K from 1 to M BK summation J from 1 to N length of FK intersection EJ. Clearly, since J and K are independent, we can interchange these sum and write it in this form. Now, since this length is equal to the summation, this is equal to length of interval Fk. So, this is equal to summation K from 1 to M Bk length of Fk, which is equal to integral over x that of function psi x dx. Therefore, yeah, we got inequality here. So therefore, phi x dx, this is less than equal to integral over x psi x dx. I hope this is fine. The main idea was to understand these characteristic functions, how they are defined on the intervals and how these intervals are related to each other, the length of these intervals.
Ma'am, in the last step, how the that will become equal to length of FK?
Uh, So if you remember in the previous section, this because this is summation j from 1 to, yeah, we did something like this, no? Wait. See, each fk, this is equal to union of ej intersection fk's. Now, if I take length of fk, that will be eventually equal to summation length of ej intersection fk. Now,
Oh,
since each
yes.
fk is pairwise disjoint, we will have the equality. I'll write it
Yes,
again.
yes.
Hmm. Okay. This happens because this fk is equal to union j from 1 to n fk intersection ej implies length of fk. This is equal to length of union j from 1 to n fk intersection ej, and this will be equal to summation j from 1 to n length of fk intersection ej, because fk intersection ei intersection fk intersection ej, this will be fk intersection ei intersection ej. This will be empty for every I not equal to j. So all the intervals are pairwise disjoint, therefore we get this equality. So we can replace this sum j from 1 to n length fk intersection ej by length of fk. Okay. Next we'll look at some converging some results of convergence over the integrals. So one result we already know that if we have uniform convergence, if we have a sequence of continuous functions that converges uniformly to a function f, in that case limit and integral can be interchanged. So, basically, we want to see whenever we can write limit n tending to infinity f n x dx equal to integral x limit n tending to infinity fn x dx. So this is our main idea. One case we already know. if we have the sequence fn of continuous functions and it converges uniformly, in that case, this will be the uniform limit, and eventually we can interchange the limit and integral. Then we have some more results over the integrable functions where we can do similar kind of things. But of course, we need some extra conditions. So one of them is the Lebesgue monotone convergence theorem. I'll just recall the theorem. Recall Lebesgue monotone convergence theorem. Now suppose Fn be a sequence of measurable functions. Let Fn be a sequence of, I'll just write MBLE, that means measurable functions, on defined on some set X such that the following holds. Firstly, we have the pointwise convergence when X for every X in X for some measurable function F. This F is some measurable function. So basically the sequence is converging pointwise to some measurable function. Secondly, the sequence is a monotone sequence. That means we have 0 less than equal to f1x less than equal to f2x and so on. This is happening for every x in x. Then in that case, we can say that this limit and integral can be interchanged. Then integral over x f in x dx limit n tending to infinity. This is equal to x limit n tending to infinity f n x, which is basically the integral of fx dx. So this is a monotone convergence theorem. Basically, we have a sequence of measurable functions that are converging pointwise to some limit, plus the sequence is a monotone sequence. That means for every fixed x, f1x, f2x. Now, if I fix this x, we know that f1x, f2x, and so on. This turns out to be a sequence of real numbers. If this is monotonic, mainly increasing, for every fixed x, in that case, we can use the Lebesgue monotone convergence theorem and hence interchange the limit and integral. We'll see some examples where we'll use this monotone convergence theorem and see how the limit can be evaluated. So let's do one problem. Let f be some function defined on some subset of R to close interval 0 to infinity. That means it is a positive function. Be a measurable function. And in fact, let it be integrable. Using this f, we will define a sequence, define a sequence of functions f and x. This is equal to n times log 1 plus fx by n for every x and x for every n and n. This is how we define the sequence of functions. Show that limit n tending to infinity integral over fx fn x dx. This is equal to integral x fx dx. solution. Firstly, try it yourself. Try to find the pointwise limit of this sequence. Find pointwise limit of f. That is, for fixed x in x, we need to find limit n tending to infinity f n x. So this is by definition limit n tending to infinity n times log 1 plus fx by n. Uh, so can you tell me the definition of Levy monotone convergence theorem? Because I don't know about it. I've read the Lebesgue monotone convergence theorem.
Lebesgue gives convergence theorem for step function also, and also for upper functions. Levy theorem for step function, it says that if Sn is a sequence of step functions
Okay.
such that it increases on interval I, and its integration when
So
entering into
basically, step
infinity
step
exists.
functions are integrable. Step functions are also integrable. So this Lebesgue monotone convergence theorem can be said to be a generalized form. Levy
Okay.
can be, yeah, that will be a special case, na? When taking the
Yes.
function fn to be step functions only. We know that step functions are measurable and integrable. Hence, that will also come into this category. So it is kind of generalization.
Okay.
This is 1 plus fx by n. Now, by property of log functions, this is limit n tending to infinity log 1 plus fx by n to the power n. And since log function is continuous, we can take this limit inside. So this is log limit n tending to infinity 1 plus fx by n to the power n. So this will be, can you tell me the limit?
And tending to infinity.
Yeah,
Log 1.
this x is fixed. This is fx upon n. We know that 1 plus 1 by n to the power n converges to e. So 1 plus fx by n to the power n, this can be written as 1 plus 1 upon n by fx, because this fx is just a constant, to the power n by fx whole to the power fx. Now this will converge to e to the power fx. Is it clear? Since fx is nothing but just a constant in this case, we have taken fixed x, so fx is some fixed constant. We know that such sequences converges to e. So if as n tends to infinity, n by fx will also tend to infinity. Yeah, so eventually this will be nothing but e to the power fx. And this is fx. So therefore, the pointwise limit of these sequence is fx. Therefore, if n x converges to f pointwise. Next, we will see that the sequence is monotonic as well. So for that, let's start with some fixed x naught. For fixed x naught, take y naught to be x naught is in x, then y naught is equal to fx naught. This is some element in this interval from 0 to infinity. Now I'll define the function gt to be t times log 1 plus y naught upon t for every t strictly positive. Now, can you evaluate its derivative and tell me whether it will have critical points and where will it be increasing, decreasing? Let's find the derivative and look for its critical points. Will it have critical point or will it be increasing, decreasing throughout? So its derivative, this will be minus y naught upon t plus y naught plus log 1 plus y naught upon t. So are you getting this derivative?
Yes, yes.
Okay. So I'll do some manipulation from here. I'll write it to be minus y naught upon t upon just dividing by t, the numerator and denominator. So this will be y naught upon t plus log 1 plus this is y naught upon t. Now I'm saying that this will be always positive because if I define another function, define h, suppose from 0 comma infinity to r, such that h at any point x, this is equal to log 1 plus x minus x upon 1 plus x. You can see that similar form here we are getting for x equals to y naught upon t. We'll see how this will be useful. So from here, the derivative of this function, this is 1 upon 1 plus x minus. So eventually this will turn out to be 1 upon 1 plus x square. You can just use the uh, rule of differentiating. So this will always be greater than equal to 0 whenever x is greater than equal to 0. Why? Because see 1 plus x will always be greater than 1. So 1 plus x square will be greater than 1 plus x greater than equal to. That would give us 1 upon 1 plus x will be greater than equal to 1 upon 1 plus x square. So eventually the derivative is positive. Since this is positive, that means the function h is increasing. in close 0 to infinity. That means h at y naught by t, this will be greater than equal to h at 0 for every t positive, because whenever t is positive, y naught we already know, y naught is nothing but f of x naught. This is also positive. So eventually this y naught by t is a positive term. It is greater than equal to 0. And since h is increasing, h at y naught by t naught would be greater than equal to h at 0. And you can see that h at 0, this is nothing but log 1 minus 0. Log 1 is 0, so this is 0. And what is h y naught minus t? This term. You know that this is equal to h at y naught upon t. And this was g dash t. This implies g dash t is greater than equal to 0 for every t positive. Okay, so from here we got this g dash t is greater than equal to 0. That means now g is an increasing function. This implies g is increasing function. That means gn plus 1 will always be greater than equal to gn. Now see, if we replace t by n, we'll eventually get the sequence, our sequence of functions that we started with. So this will be n plus 1 times log 1 plus y naught upon n plus 1 will be greater than equal to n log 1 plus y naught upon n. So that means now since this y naught was fx naught, this is just n plus 1 log 1 plus fx naught upon n plus 1. This will be greater than equal to n log 1 plus fx upon n. Yeah, we can, okay, we'll write this as x naught. This is happening for every n in n because g was defined for positive real numbers. This is happening for every n in n. Okay. Now this tells us, now since x naught belonging to x was arbitrary, we get f1x, this is less than equal to f2x, and so on, fnx on. And yeah, obviously this sequence is sequence of positive functions because f1, what will be f1? Yeah, f1x, this is just log 1 plus fx. Now since f is a positive valued function, this 1 plus fx is greater than 1, so eventually this will be greater than equal to 0. So hence the sequence of functions fn, the sequence fnx converges pointwise to the function fx, and also it is monotonic sequence. Therefore by Lebesgue monotone convergence theorem, therefore by Lebesgue monotone convergence theorem, we can interchange the limit and integral. Limit n tending to infinity, integral over x, fn x dx. This is equal to integral over x, and the point was limit was fx. Please go through the solution again and let me know if you have any doubt at any point. So the main idea was to show that the sequence of functions is monotonic and its pointwise limit is the function fx. Hence we use the Lebesgue monotone convergence theorem.
And how this function fnx is defined here?
Fnx, this is the definition.
So,
Fnx
mm,
is n times log 1 plus fx by n.
so first we have shown that it is pointwise convergence.
Yeah,
And
its pointwise limit is the function fx itself. And then we show that the sequence is monotonic. Basically, it is increasing. For that, taking n to be some other variable t, I proved that this function gt, which is t times log 1 plus fixed fx by t. Now this, if this function is increasing, so eventually we'll get that gn plus 1 will be greater than equal to gn. That's what we want for every fixed x.
mm,
So in order to prove that this is increasing function, we have shown that its derivative will be positive everywhere. Okay. Then next, another big good theorem about this interchanging of limit and integral is the Lebesgue dominated convergence theorem. So we'll be using that in order to prove next problem. Next question. So we have compute the following limits. This one. Limit n tending to infinity integral 0 to 1 plus n x square on 1 plus x square to the power n dx. Secondly, we have limit n tending to infinity integral over 0 to infinity n sine x by n times x into 1 plus x square to the power minus 1 dx. So these problems might seem very complicated, but if you are good, well aware about of the dominated convergence theorem, you'll see that these are very easy problems. So yeah, I'll just recall the Lebesgue dominated convergence theorem. Let Fn be a sequence of integrable functions functions defined on X and the following holds. Firstly, there exists an integrable function I'll just comment 2 minutes. Okay. there exists an integrable function f such that it is the pointwise limit f in x to f in x converges to fx for every x in x. Secondly, there exists some dominating function. There exists an integrable function. So in this case, we need some other dominating integrable function as well. Yeah, integrable means Lebesgue integrable. Integrable function g such that mod fn x is less than equal to gx for every x in x and n in n. So this function is called the dominating function. So basically, we need pointwise convergence as well as existence of a dominating function. In that case, we can interchange the limit and integral. Then limit n tending to infinity, integral over x, fn x dx. This is equal to integral over x, fx dx. So yeah, is this definition clear? Yeah. In previous session, I had explained this. Now, since this has become a part of your syllabus, so I think you're more comfortable with these terms now. And this is a very good result, dominated convergence theorem. Mostly, you'll be able to solve problems related to this convergence of integral using this Lebesgue dominated convergence theorem. So yeah, we'll see above examples. So in first part, we have fn x. This is equal to 1 plus nx square upon 1 plus x square by n. This is 1 plus n times x square upon 1 plus x square whole to the power n. So please find its pointwise limit. Limit n tending to infinity fn x. I'll come back in 2 minutes. Please evaluate its pointwise limit. Okay, so you are getting 0 as pointwise limit. So yeah, using L'Hopital's rule for x equals to 0, this will be 1. Yeah. So we can say that this fnx, it converges to the function fx, which is equal to 0 when x is non-zero, and this is equal to 1 when x is equal to 0. Good. And what about a dominating function? Can we find, yeah, clearly this is integrable function. We know that obviously 0 to 1 fx dx would be 0 because that one point doesn't matter that much. Then next we need to find some dominating function. Now this for x belonging to closed interval 0 to 1 mod fn x, this is equal to mod 1 plus n x square upon 1 plus x square to the power n. This is less than equal to 1, because obviously 1 plus x square to the power n, when you expand using binomial expansion, its first two terms will be 1 plus n x square, and then we'll have some positive more terms because we are taking this x to be a positive real number. So this will be eventually less than equal to 1. And since integral 0 to 1 dx, this is one a finite number, we know that this function, if I write gx equals to 1 for every x in closed interval 0 to 1, g is integrable. And hence this constant function 1 will work as the dominating function. Hence by this dominated convergence theorem, integral 0 to 1 fn x dx, this will converge to 0. Similarly, we can look at second part where we have fn x, this is equal to n sine x by n upon x1 plus x square. So yeah, find its pointwise limit. We have limit n tending to infinity fn x is, I can write it as sine x by n upon x by n times 1 plus x square. We know that this will tend to 1 as n tends to infinity, because as n tends to infinity x by n is going to 0, and we know that sine x by x for x going to 0, this converges to 1, and rest of the term is independent of n, so this will
1 by 1
eventually
plus x square.
yeah, 1 by 1 plus x square, and we know that clearly this is is it
Integrable.
integral? So our domain of integral is 0 to infinity. Since 0 to infinity dx upon 1 plus x square, this integral is
Sine tan inverse x.
tan inverse. Tan inverse x 0 to infinity, and we know the tan inverse infinity is pi by 2. So this is pi by 2 minus 0, pi by 2. This is finite. Therefore, this function is integrable. This will be our fx, and then we'll find the dominating function fn x. This is again sine x by n upon x by n 1 plus x square. this is less than equal to, we know that mod sine x is less than equal to mod x. So this is it as mod x by n. So yeah, for positive x and positive n, let's not take this mod. That's same, x by n upon x by n times 1 plus x square. So this will get cancelled out. This dominating function will also be 1 plus x square. This is happening for every n in n and x in 0 to infinity. We know that this gx equals to 1 upon 1 plus x square is integrable on close 0 to infinity. Therefore, in this case, the dominating function and the limit function both are same, and hence by dominated convergence theorem, integral 0 to infinity fnx dx, this will converge to 0 to infinity fx dx, which is nothing but pi by 2, because fx was this 1 upon 1 plus x square, and we know that its integral from 0 to infinity will be pi by 2. So I hope this is clear how we use the dominated convergence theorem. If we compare it with the monotone convergence theorem, it is kind of more easier to deal with, because for monotone it's many times it's difficult to see get this sequence to be monotone. That would be a very specific case, but finding a dominating function would be comparatively easier task. So that's why this dominated convergence theorem is, yeah, it's a good result. So after this, have you read something about the LP spaces? So basically, these integrable functions are called the functions in the L1 space. So instead of writing that these are integrable, we say that this G belongs to L1 0 to infinity. Okay, it's okay if you haven't done, maybe you'll do that in uh, upcoming classes. So, yeah, for the time being, I'll explain. We have LP spaces, LP over X. This is the set of all those functions such that, I think I had explained this earlier also, mod f to the power p. This is finite. Basically, mod f to the power p is an integrable function. This is collection of for every p greater than 1. You'll go see what happens for the case p less than 1. Collection of all measurable functions such that mod f to the power p, this is integrable. So instead of writing everywhere this, suppose when we were talking about this dominating function. So instead of saying that there exists some integrable function, we say that there exists some L1 function. So yeah, then we have a very good inequality. We call it the generalized Hilder inequality and Hilder inequality. I wanted to explain its proof. Let's see. Question. Let f belongs to LPx. That means mod f to the power p is integrable over x, and g belongs to some LQx. That means mod g to the power q, this is integrable over x. R greater than 1 be such that R is some real number. It satisfies the condition 1 upon p plus 1 upon q is equal to 1 upon r. Then this function h, which is just f times x. This is just pointwise multiplication, not composition. This belongs to LR with, okay, so then we have norm, okay, to be with integral mod integral over x of h to the power r whole to the power 1 by r. This is less than equal to integral over x mod f to the power p to the power 1 by p times g to the power q whole to the power 1 by q. And this inequality, this is called, so instead of h you could have written f times g. So this inequality, this is called generalized Hilder inequality. This is also a very good result. Then show that this is okay. So now since f belongs to LP and g belongs to LQ, we have, since f belongs to LPX and g belongs to LQX, this implies integral over x mod f to the power p whole to the power p. This is some finite quantity because mod f to the power p is integrable, and mod g to the power q whole to the power 1 by q. This is also finite quantity. Also, I'll assume that these f and g are non-zero functions. So yeah, so modulus of that will be strict. So the integral would be strictly positive.
It is less than infinity because the consequence of definition of
Yeah,
f is in L2.
less than infinity. This means this is a notation to say,
Finite.
yeah, to say that it is finite. Finite. And see the definition of LP space in the, if from here we can see that since f belongs to LP, that means mod f to the power p is integrable. That means this integral, this is finite. Clear?
Yes, ma'am.
Okay. So yeah, these are finite. Now this is a fixed real number, so I'll define another function. Define a function fx. This is equal to, this is fx to the power r upon this fixed mod f to the power p equal to the power 1 by p. This denominator is nothing but just a constant, and we know that this is non-zero. So this implies integral over x mod fx to the power p by r. Now this is taking power p by r in the definition of capital Fx. This will be small fx to the power r upon mod f to the power p whole to the power 1 by p to the power p by r
How it was
dx.
non-zero?
Because I have taken this function, these functions, I'll write it here. F and g are non-zero functions. Since they are non-zero functions, the this mod f is a strictly positive function, and hence the
Mm.
integral will be positive.
Okay.
So this will be equal to integral over x mod fx to the power p upon integral over x mod f to the power p. This power 1 by p and p will be cancelled out. This will be just 1 by r. Now this denominator is just a constant. I can take it outside. This will be 1 upon. Okay. So yeah, in this definition, this is r by p. R by p. So this will be just 1. Yeah, this denominator is a constant. I can take this outside. And this is mod f to the power p dx. So everything turns out to be 1. Similarly, I define capital Gx. This is small gx to the power r upon integral over x mod g to the power q to the power r by q. Hmm. Then also again we'll get mod g x to the power q by r. In the similar way, this will turn out to be equal to 1. Now this f and g, capital F, capital G, are two real valued functions. So since capital F and G are real valued functions, this implies for any fixed r, for any fixed x in r, there exist two real numbers s and t in r such that I can write fx, capital Fx, to be equal to e to the power s r by p and gx to be e to the power t r by q. Now this is happening because f and g, I think I should have taken positive because exponential will give us only positive value. No? Yeah, let's assume these f and g are positive, then we can generalize it for 0 as well. F and G are strictly positive functions. Yeah. And in that case, this capital F and capital G will also be positive valued functions. And we know that this exponential function takes all positive values. So now, since this fx was some positive real number, clearly I can find some s and t such that this can be written in this exponential form because the range of exponential function is the whole interval 0 to infinity. Sorry, 0, open 0 to infinity. Yeah. So I hope this is clear how I can write because this x is fixed. I can write this in this form, exponential form. We'll use the convexity of convex exponential function. That's why I'm writing it in this form. We know that the exponential functions, yes,
Then every real number is e to the power something. So
every
that
positive real number.
yes, every positive real number,
Hmm.
and how that the power is in the form s into r by p, that is specific form.
It can be in any form. Now, suppose fx was e to the power y naught. Okay. So I want to find some s. See, r and p are fixed. I can write y naught to be s r by p. In that case, s will be p times y naught by r. We know that such a y naught will clearly exist. I'll write that y
Oh,
naught equals to s times r by p, because r and p are constant, fixed
R
in the
and P are
starting instance.
fixed.
Yeah, r
Okay.
and p are fixed because we started with p and relation between pq and r. These pq and r are fixed. I'm saying that then I can find some s and t that will satisfy this condition. We can take this s in this form.
Yes, ma'am. Okay, thank you.
So next we'll use the convexity of the exponential function. We know that the exponential function is convex. Since e to the power x is convex function, we can write e to the power s times r by p plus t times r by q. This is less than equal to r by p e to the power s plus r by q e to the power t, because this r by p plus r by q, this was equal to 1. We started with this relation between p, q and r. We had 1 by p plus 1 by q is 1 by r. So basically r by p plus r by q is equal to 1. And we know that for convex functions, if suppose this function h x was e to the power x, by convexity of the exponential function, I can write r by px plus r by qy. This will be less than equal to r by p times h of x plus r by q times h of y. Yeah, that's what I have done here. Is it clear?
Okay. This is the definition of convex function. Okay.
Yeah, yeah. Exponential functions are convex function. That would be a good exercise. You should see how this is convex function. How these exponential functions are convex. And you can look for other examples also. I think x square, x square, x to the power p. Such functions are also convex.
Okay.
Hmm. So now this is e to the power s r by p plus t times r by q. This is nothing but e to the power s r by p times e to the power t r by q, and that is fx times gx. This is less than equal to r by p e to the power s. Now this e to the power s, from here you can see that fx to the power p by r, this is e to the power s. Similarly, from here, gx to the power q by r, this is equal to e to the power t. So from here, this is less than equal to r by p times e to the power s, and e to the power s is fx to the power p by r plus r by q times gx to the power q by r. Next, we can integrate both sides. We know that as done for the step functions, you can do that for general integrable functions. If fx is less than equal to gx, then their integral also holds the same inequality. So this implies integral over x fx gx. This is less than equal to integral over x r by p fx to the power p by r plus r by q gx to the power q by r. Then this is equal to r by p integral x fx to the power p by r. And since everything is positive, we can take the modulus. And this is equal to, so we had seen that mod f Integral of mod f to the power p by r, this was 1. Integral of mod g to the power q by r was also 1. So this is just r by p plus r by q, and which is equal to 1. Now let's get back to how we define this capital F and capital G. Yeah, this implies integral x fx gx, this is less than equal to 1. Capital F is f to the power r upon integral mod f to the power p whole to the power r by p. So this is fx to the power r upon x mod f to the power p whole to the power r by p, and this is gx to the power r upon integral x mod g to the power q to the power r by q, and this is less than equal to 1. Now this denominator term is independent of x. We can take this outside, and since everything is positive, we can just cross multiply. So eventually this will be fx gx. Since this is positive, I can take this modulus. This is less than equal to yeah, that's what we wanted to show. Since f belongs to LP and g belongs to LQ, this is finite. Therefore, this function f times g, which was hx, is in LR, and further it satisfies this inequality. So the main idea was to use the convexity of the exponential function. Good. So now it is clear how we get this generalized Hilder inequality. This is used at various places. So you'll come across this inequality a lot of times. So it's good to see the proof. And the proof mainly uses the, it's kind of manipulating everything eventually to get what we want. And main idea was to use the convexity of the function e to the power x. There are some other ways of proving this. I think I have seen one more method. Yeah, but this one seems very easy. All, yeah. Eventually, you just need to manipulate everything to what to get what we want. Okay, so I hope this is clear. Okay, then see some related problems in next class. So we are left with 2 more sessions. In next session, yeah, hopefully we'll do some similar problems or whatever that would be done by that in your theory classes. Okay, then. Yeah, if you want me to explain something related to theory or something else, so that I'll be prepared. Hey, you can unmute yourself. The questions are hard, I know that. What can we say? You are doing masters now. Okay, so questions, you mean that the assignment problems?
Yes.
Okay, so maybe we can do one thing. The assignment which due date is gone, I can discuss that assignment then.
Yes, ma'am, please.
So tell me which assignment you want when I'll have to see the solutions. Um, Let me see. So week 11 is the latest one, na?
Yes, ma'am.
Its due date is on 10th, 8th October. Okay. Week 10.
Yes. Okay.
Week 10, the
Yeah,
due date is on 1st October. So maybe, yeah, we can discuss this week 10 assignment. There are just three questions. Yeah, they are also related to these, the sequence of functions.
yes,
Yeah,
ma'am.
we'll discuss this assignment 10 after your due date is over. We'll have class, yeah, after 1st October. Okay, I'll look at these problems. And anything else specific in previous weeks
So I try to understand the lectures delivered by sir on
on
uh,
Lagrange theorem?
Levy monotone convergence theorem and for Lebesgue integrable function for upper function for step functions.
Okay. Yeah, that's all what you did in week 9, na?
Yes, ma'am. Week 10. Week
Yeah,
9 starts from Lebesgue and
yeah.
some basic of Riemann integral.
Okay, then we'll do problems of week 10 or week 9 also.
Actually, sir is doing uh, वो कर रहे हैं कि हर चीज को और छोटा करके बता रहे
छोटा करके मीन्स और डिटेल में?
हैं डिटेल में नहीं बता रहे वो उसको इलेबरेट करने की जगह और ज्यादा जैसे बुक में लिखा रहता है हम
No,
वैसे
because he's taking theory classes, na? In theory classes, he'll have to explain everything in detail. These are tutorial sessions. That's why we discuss just the problems. Tutorial
यस
sessions are meant to discuss only problems, and there, yeah, he'll have to explain everything in detail because you are attending the classes regularly. He doesn't know the level of other students, na? Okay,
नो
so we'll
नो मैं उल्टा कह रहा हूँ सर जो है ज्यादा उसको ई कर रहे हैं वो क्या बोलते हैं उसको
difficult.
हम्म
Okay, wait a second. Let me stop recording.
बुक्स में तो स्टैंडर्ड मेंटेन रहता है लेकिन सर का स्टैंडर्ड तो और ज्यादा हाई रहता है